All right, welcome back. So now here we are, we're in lesson 4, and we're going to deal with our first data structure that is not a data type. We looked at what a list was, we looked at what an array is. Those are things that we've dealt with in the past. The main difference between the two are that an array is sequential in memory, not just sequential items stored one after the other. Logically, they're stored one right after the other physically in memory. Whereas a list is logically one after the other, but physically they're not. They don't have to be. They may be, but they don't have to be. Aside from that, an array is all the same data type. A list can be just about any data type. So what we're going to talk about in this lesson are linked lists. And there's a variety of different types of linked lists. There's singularly or singly linked lists, doubly linked lists, and circular lists. Now, for the sake of discussion, how we're going to look at this, I want to look, the analogy I want to use is a boxcar from a train. So, picture in your mind at this point a boxcar that you would see in a train. And these boxcars have a coupling at the front and they have a coupling at the back. They can connect to another boxcar ahead of them and they can connect to a boxcar behind them. So with that point in mind, we're going to think about items in our list. Each index in our list is like a boxcar. Now, if we're thinking about a list as it relates to a data type or a data structure, just a standard list, we've got this data type that it's like a string. It holds in it a bunch of different values. It's sequential in structure and it's got different values in each one. And the list, what's in it, is a pointer to that location in memory where to go get what it is you're looking for. So it's referencing where the value is. Different than an array, because you know where the next one is. It's right behind it. So we're looking at a list, and the things that are in the list can be stored just about anywhere. I need their reference, their address, or I need a pointer to where to go get what I'm looking for. So a list is just a bunch of different pointers pointing to where to go find what would be in that bucket if it had to be right next to each other. So let's talk about linked lists. So here's our list, index 0, 1, 2, 3, 4, 5, 6, and the things that are stored in there. Well, index 0 points to that place in memory. Index 1 points to that place in memory. And so on, and so on, and so on. This is a one-dimensional array. And when we come down and we look at what's happening here in this linked list, I'm going to say here's train car A, boxcar A, and here's boxcar B. And this is the first one, and we can add more to it. And this one has a pointer telling you where the next one is. So we're looking at things a little bit different. Instead of we have this list of all these addresses, here's where to go find A, here's where to go find B, here's where to go find... We don't have that. In this one, I've got in this first boxcar, I've got actual data in there. And there's also another little tidbit that's stored in there along with it, which is a pointer to the next boxcar. So here's the boxcar, and in it there is a payload, and there's also a pointer to the next boxcar. We get to the next boxcar. Oh, there's your data. And we've also got pointer to the next boxcar. Now, this is a logical structure. This isn't a physical structure. Because we know that the data is not actually here. The data is somewhere else. So in essence, it's two pointers. But this, logically, we're saying, oh, I've got this boxcar, and I've got some payload in it, and I've got a pointer going to the next boxcar. Payload, pointer going to the next one. Oh, wait a minute, there is no next one. And then it says nothing. The pointer going to the next one says we don't have anything behind us. So that's the logic there. The only thing that I'm missing is something to identify this as the head, or the front of the train. So each one is a node with a pointer to the next node. This node has data. Now, remember what I said before, these are actually pointers. Well, here's how this looks more real when we're talking about the physical structure was taking place. In a list, it would point to where the data is. We've also got another pointer pointing to the next node. Points to data, points to next node. Points to data, points to next node. And we keep going. We keep going. If you want to add on, I can take another node and I plug it right in here, and all I have to do is modify this pointer to point to it. Easy. What if I wanted to put a new node in here? Well, I take what's in this one and I put it in my new node, put a copy of it in my new node as a pointer pointing to this one. And then I replace what's in here with a pointer to what I've inserted. Keep in mind, each of these is somewhere different in memory. And these are all in different places in memory. So these are just little bits all over our RAM. So there's a bunch of pointers going on here. But here's a boxcar, another boxcar. I can squeeze a boxcar in between, but to do it, I need to point to the new one and have the new one point to the one that's going to be behind it. You should be okay with that logic. This isn't a huge stretch. So we got a class called a node, and the node has data associated with it. Yeah, right there, we know that. And the node has another payload in there that is next. What is the value on next? Well, by default, it's none. See, right there, by default, it's none. I can set that value to something and say, well, it's point to this one. But here's the basic class of a node. And we would need this just to be able to get started on this data structure. So here's the definition of just one node. And if I have one node, I can create multiple instances of a node. Node A, node B, node C. Each one's going to have different data in it. And each one's going to potentially have a pointer to what's behind it. So that's this singly or singularly linked list. And as we go through it, at some point we're going to have one that's identified as the head, and from that one, and the head is when we go to find our linked list, singly linked list, it'll point us by default to the head. So we go look here, go find the next one, go find the next one, go find the next one. So if I want to navigate it, I have to go from the front of our sequence of boxcars one by one to the back. I don't jump in between because I don't know where these others are until I get to the one before it. You all right with that logic? I don't know where this train car is on the train until I get to the one that points to it. The only way I know where any of these are is because I've gone to the one ahead of it and I got a pointer telling me where to go look for it. Because keep in mind, these are not like an array where they're physically sitting right behind it. If it was an array, it would be sitting physically behind it, but it's not. We're looking at a list. So if that next train car is physically somewhere else, but logically it's behind it. So when I create it, I create my head, and then I'll create another instance of a node, another instance of a node, and those are the cars that are behind our head node. And N1 gets a next value pointing to N2. N2 has a next value pointing to N3, and now I have a sequence of 3 nodes. Works. Here's a way for me to find out where I am. I start out at the front, and I work my way to the back, one by one. When I get to the next one, I modify current to be the next place I'm at. Print out what's in there. Go to the next one. That's our current one. Print the data. Go to the next one. Go to the next one. So there's our logic to traverse it. Okay. Start at the beginning. We get in the loop, print the data, change our position to be from where we're at to the pointer or the destination of the next one. What's behind it? Go to what's behind it. Go to what's behind it. Well, I said behind it logically, not physically. Okay. So I can go through and I define the first one as the head. I can go through and I've made creation of my singly linked list, improved it. This helps me iterate through it. So I start at the beginning, work my way back. One way to go through it. For word in words.iteration, so that's iterating through a sequence, print each word. Okay, that's iter method allows us to walk through step by step by step by step a list. So it's a built-in method within this logical structure that allows us to go step by step by step all the way through. We need it. Without it, I can't work my way from front to back. I want to go through each one of them. And for me to go from the front to the back of this singly linked list, I need a structure or a function method that allows me to do it, to walk through them, item by item by item. I can't jump from one to the next. I have to go through them sequentially. This method allows me to do that. Now, for me to append, well, that's easy. I go to the last boxcar in our train, and I change the next pointer to point to whatever I'm adding on. So I've got to create the new node. Once I've created the new node, I have the pointer, I create a pointer for where it is. I go to the last node that's in our linked list, singly linked list, and I change that last item to be pointing to our new one. So that's our way to append. Append is adding to the end. Insert, we add something into a list. Append, we tack it on the end. Okay? So appending goes to the end of the list. So we'll have an append function or method that works our way all the way to the end. And if we have found the end, and how do we know we found the end? We looked at next, and next didn't have anything in it. Okay. So the logic there, we work our way, find out where the end is, and this structure will allow us to walk from beginning all the way to the end. Okay. Now, here's the logic of it. I've got our head. We go through. Is there a value in this pointer? If no, plug it right there. Oh, there is. Oh, there is. Oh, there is. Oh, no, there's not here. Let's plug that one right in there. Now, that's appending. I alluded to how we would go about adding something in, inserting it. Here's the append. And how do we know it's the tail? Next has no value in it. So if I want to, and they say append at intermediate positions, that's inserting. Append is on the end. We want to insert. So to insert, and I told you how we're going to go about that, I need to know which one's it going after. All right, it's going after this one. I copy this value, paste it here, get this one's physical address, and paste it here. Now I've slid this one right in the sequence, logical sequence. And here's Python code to go through and do what we need to do navigating this linked list, singly linked list. Here's our insertion, or they say append at a location. Where is it that you want to insert? I want to insert after a specific piece of data, which is I look to see what's in that payload for that node. So if we were sorting out the contents of this singly linked list based on their value, well, it would go through and do comparison, see if it's high or low. Or if we were looking to go after a specific node with 256 being stored in it, that's, once we find 256, get the pointer for 256, write it in our new node, get the location of our new node, write it in 256. That's our append at location, or as I would prefer to call it, insert. So how do we go through and look to see what's in each item? Well, I iterate through. It's using the iter method. For node and self.iter. Self is our singly linked list. We're going to iterate through it. So we've got this class that we've created. We're an instance of it, self. For each node in it, we're going to go through and look to see what's what. Is this what we're looking for? Is this what we're looking for? How do we know the size of a list? Well, that's easy. We just iterate through it and aggregate as we go through. Count one by one and add that number up as we go through each one. How do I delete an item? Well, it's not so bad, because this one points to this one, this one points to this one, this one points to this one. If I want to get rid of this one, I said, well, I need the one before it. I need its pointer. So I've got the location. This one points to this one. I want to get rid of this one. And I've got this one. I know that we point to this one. So all I need to do essentially is get this one's address so that I point from here to here. And if I skip right past this one by making the pointer to this one go to this one just falls away. That's it. That's logically how I delete a node. We just ignore it. It's not on the route anymore. If we think about that Amazon comparison, all right, here's the things you're going to deliver. They canceled their order. You're going from here, and here's your next one, next stop. That's all it happens. Now, if you said, you know what, let's delete the head. No problem. When you go to the structure, instead of going to this one, whatever this head pointed to is now the new head. Okay. Delete the node at the end. That's simple enough. I go to the last one. So as I'm working my way through, I'm storing the address of the predecessor. I'll have a little temporary variable that I store the address of the predecessor. And if I go from this one to this one and this one doesn't have anything after it, I know that this is where I'm going to go back to, and I'm going to delete that pointer pointing to the next one, delete it off of here. So now this one has a next of none. It's the last one. Now, this seems simple enough. We go about the same concept to delete something within. Same thing. I get the address here, and I write it in here. So I'm pointing from here to here. Now this is gone. So this is a singly linked list. And if I want to get rid of the whole list, if I don't have a head, when I say, hey, point to that list, well, if there's nothing that it's pointing to, then there is no more list. I didn't have to delete all the things. I just said, head's gone. So the name of the list points to that head. If that head's gone, the name of the list points to nothing. It's empty. It's been cleared. Okay. Tail is none. Head is none. So the difference between a doubly linked list and a singly linked list is the fact that there's an extra payload in the doubly linked list. And the payload is not only are we pointing to what comes after it, we're pointing at what's ahead of it. The head doesn't have anything to point to. The tail doesn't have anything to point to this way. How do you know which one's which? By that. Now, at a certain point, as we move forward, with this one, I can navigate both ways. It makes it a little bit easier. I don't have to have that temporary storage that I had before. But I've got more I need to change when it comes time to insert or delete. Because now I'm not just looking at what's coming after it, and what's before it. So it's a little more efficiently allowing us to move back and forth, but I've got 100% more pointers involved in this thing. Twice as many. So here's the structure to go through, code structure to go through and create a node that not only has next, but it's also got previous. And it's got the payload of the data. Very similar to what we just dealt with. So that's a doubly linked list. We have head, tail, and how many's in it. We'll use iter to work our way through it. Append works the same way. If I want to append, I go to the last one. I know that there's nothing after it. I take my new one, and the new one has none and none. The tail will now point to my new one. I go to it, the new tail points to the previous one, which was the tail. So logically, it's very similar. We're just having a little bit more work to do on the doubly linked list. Now, what if the appending and all that, it's almost the same as what we were talking about before. The plus is I can iterate through back or forth. Delete works the same way, except I've got to modify what's in front of and behind it now. And we've got one more type that we haven't dealt with, and that's circular. And circular, we've got a head that points to the next, but the head also goes back and let me back up. Circular on this one is not a doubly circular. This one is a singly circular. So this one we point to the next, and at the tail it says, all right, here's how you get back to the beginning. So next on the tail points back to the head. Here's the doubly. The next points back to the head. The head says, all right, here's the tail. And then there's code to go through and do the same. It's very similar to doubly. The only difference is data at the front and the back, or the head and the tail, are not null. It's the only difference, really. how we go about navigating them is about the same. Okay. They give some examples of how would we use it. Dynamic memory management. A sparse matrix. Think about it, it's almost like if I'm in line, I'm in a queue. A queue's different, but if I was in line, I don't necessarily have to know who's behind me. All I need to know is who's in front of me. All right, that's a singly linked list. Just need to know who's in front of me. I know they're ahead of me. As soon as they're gone, now I'm in front. If I need to know who's in front of me and who's behind me, well, doubly linked list. The circular part doesn't come into play if we're kind of comparing it to some kind of queue. But that's the logical structure of what we're talking about with linked lists, whether it's singly, doubly, circular. Conceptually, it's not brutal. We look at it from the standpoint of we're talking about a boxcar is on a train. What boxcar is connected ahead of you? This one. That's a logical connection. It's not a physical connection. So with that said, see you next go. Get familiar with these snippets of code. Let's see if I can plug in some resources for you relative to notebooks for each type of structure.